All right, welcome back. Today we're going to discuss the notion of area between two curves through the lens of an example, ultimately furthering our understanding of the topic as we've seen so far. Just to remind ourselves of the concept, we're looking at a region not beneath one function or beneath another function, but rather between two functions. And the way that we could think about this perhaps is to say, well, the area of the region between the two functions is not the area beneath the top function. No, it's the area beneath the top function with the area beneath the bottom function taken away. So this ultimately results in an expression formulaically of the integral between the two bounds of interest of the top function minus the bottom function dx. I think it's nice to use top and bottom here as opposed to f and g because depending upon the situation, f may be the top function or g may be the top function, or we might not even be dealing with functions labeled with f and g. So referring to the top function, the bottom function by top x and bottom x, I think makes a lot of sense. Now, to take this one step further, one thing that you will certainly see, and in fact we'll definitely see here in an example, is what we call the area enclosed by or the area bounded by two curves. So here's a picture of just a function f and a function g, and I've sort of denoted through shading the region that's enclosed by. The region that's enclosed by is the area that lies between the two intersection points. There are other regions of the plane that are defined by these functions. There's like a region off here to the left, or a region off here to the right, or a region up above or below, but that region that's like to the far east or the far west is infinite. The region to the far north or the far south is infinite. Only the region sort of between the intersection points is of finite area. And so if we're going to be computing the area of a region that's sort of enclosed by, it kind of makes sense that the region that's enclosed by is not the area that runs away to infinity, but rather the area that's between the intersection points. If we want to find the intersection points, which I've denoted here as x1 and x2, note what's occurring at x1 and what's occurring at x2 is that the two functions are evaluating identically. To the left of x1, it looks like the function g is evaluating above the function f, but the two functions are not evaluating identically. Only at the intersection points are the evaluations equal. And so if we ever want to solve for the intersection points, which we certainly do if we're trying to find the area enclosed by, which lies between the intersection points, what we do is we just set f of x equal to g of x. So literally setting the two equations expressions equal to one another and solving will allow us to find the x's that correspond to where the two functions evaluate identically, where the two functions' graphs intersect. Looking between the intersection points, then, we could isolate the area that's enclosed by two curves. So taking a look at this example that we've got articulated above, we're going to try to find the area of the region that's enclosed by the function f of x equals x squared plus 2x plus 5, and g of x equals 4x plus 8. So if we want to try to find the area of a region enclosed by, we start by looking at the intersection points. And to compute the intersection points, we just take the two functions and set them equal to one another and solve. So the x's for which the equation f equals g is true are going to be the x's where the two graphs intersect. Well, as we've seen in our mathematical past, when you have polynomial equations such as this, it's often easiest to bring everything to one side and try to factor so that you can sort of have a multiplication expression equal to 0, because when two things multiply to be 0, one of them must be. So here we go. Let's see. Well, since the x squared is positive on the one side, the left side, namely, let's pull everything to the left side. So subtracting 4x from both sides, we'll get x squared minus 2x, and subtracting 8 from both sides, we'll get minus 3 equal to 0. So again, this is what we were after. We want this thing equal to 0 so that we can factor, and in fact, this factors quite nicely to x minus 3, x plus 1 equals 0. And then looking at this, you can see that if you plugged in x equals 3, you'd get 0 times something, which would solve. And if you plug in x equals minus 1, you'd also get something times 0, which would solve the equation. So ultimately, we've got x equals 3 and minus 1 as our intersection points. So our region that is enclosed by our two functions lies between 3 and minus 1. However, looking at our area region, so I guess we could use our area region computation to know that in this case, we have an integral from minus 1 to 3 of the top function minus the bottom function dx, which sort of begs the question, what's our top function and what's our bottom function? Because, well, we haven't taken the time to assess which function is on top or bottom yet. And so how can we do that? Well, we know we're looking between minus 1 and 3, And then what we could do is simply just evaluate our functions between -1 and 3. At any point between -1 and 3, the one function is going to be above the other because the functions are only coinciding between, at x equals -1 or at x equals 3. So in between, one of the functions is going to be on top. So if we plug in a value between -1 and 3 to both of our functions, the taller evaluation is going to be the top function. So we could plug in any number between -1 and 3. I'm going to plug in 1. Why not? 1 is between 1 and 3. We also could have plugged in 0. We could have plugged in 2. We could have plugged in a half if we wanted, but I'm going to try to keep it computationally simple. I suppose 0 would have been as simple as possible, but so be it. Here we are. So 1 squared plus 2 times 1 plus 5. The function f evaluates to 1 plus 2 plus 5. That makes 8. And what about g of 1? That's going to be 4 times 1 plus 8. And hey, I can see that's more than 8 straight away. So we know we've got our top function in the form of g and our bottom function in the form of f by virtue of the function f having a graphical point at 1, 8, whereas the function g had a graphical point at 1, 12. Of course, 1, 12 is higher than the point 1, 8. And so plugging into our area region computation, the top function would be g, which is 4x plus 8. And the bottom function is f, which is x squared plus 2x plus 5. By the way, you'll know whether or not you've done this correct in terms of finding your top and bottom function as to whether or not the result that pops out of this computation is positive or negative. The area should be positive as a result of our considerations for which is on top and which is not. Let's see, 4x minus 2x, that's going to be 2x. 8 minus 5, that's going to be 3. And then we got the minus x squared. And, well, to integrate this, what do? We ultimately find the antiderivative. That's x squared plus 3x minus x cubed over 3. And I'm going to refrain from plugging in the values here because, well, that's just a matter of computation. But we know we could just plug in the 3, plug in the -1, and evaluate. And we will get what we do. Forgive the pause there for a second. I just took a moment to effectively plug this integral in and compute, and the resulting value should be 40/3. So if you're working through the computation on your own and want to double check that you're accurate, the result is 40/3. But the big idea here is that in general, when you find the area between two curves, you need to isolate which function is on top and which function is on bottom. You also need to isolate what the bounds are for your region of interest. Should you be looking at a region that's enclosed by or bounded by two curves, you're going to be looking at the region between intersection points. And should you ever have to find intersection points, you just set the two functions equal to one another and solve for the x's where the two functions evaluate identically. Yeah, that's really, in a nutshell, the nature of area between two curves. And through more examples and more work, I suspect our knowledge of this topic can be quite solid.